Okay. The previous half of the semester we have devoted to thermodynamics. And from what you have seen about this subject, you see that mostly thermodynamics doesn't rely on any assumption about the inner structure of the matter of we study. Mostly we use some observations, and also the subject is heavily based on multivariable calculus. So we apply the power of multivariable calculus to observations, and then we are able to arrive to some results. So in essence, the subject was designed in such a way that you don't need to understand the inner structure of systems you study. Today we are going to start with molecular physics. And this subject works in a completely different way. This subject aims at understanding of underlying principles about structure of matter, which allow you to understand the phenomena in thermodynamics on a different level. So you can say that all of these thermodynamic phenomena can be explained by a complex and chaotic collective behavior of atoms and molecules. And in order to understand it, we need to design a new language. So if thermodynamics can be said to be written in multivariable calculus, then molecular physics is based on a completely different subject, which is called probability theory. So this is a mathematical basic. So today we are going to discuss some kind of alphabet in terms of probability theory, which would allow you to understand the topics of molecular physics. So probability theory starts when we consider some kind of a system in which we have some chaotic unknown results. For example, when you flip a coin, so you can have one of two different results, which you can denote as 0 and 1, depending on the side on which the molecule flips onto. And then all of results of your flipping can be denoted as a sequence of zeros and ones, which represent the results of your flipping. It's the most simple system, but nevertheless it can be used to illustrate quite complex concepts of probability theory. For example, you know that if coin is fair, then the probability of each of these results is equal. So you can say that probability to have 0 is 1 over 2, and probability to have 1 is also 1 over 2. You can note that the sum of these probabilities equals to 1. So you can say that the probability to have some result after you flip a coin is identity. So you would show it to have some kind of a result when you flip a coin. This equation is called normalization condition. Normalization condition. Or you can say that if you introduce some quantities which you will further call probabilities, then you should design them in such a way that the sum of the probabilities of all possible events in your system should be equal to 1. So in this way, this probability distribution can be called normalized. So this is one of the most important properties of any probability function. At the same time, if you want to answer a bit more complex questions about this sequence, you need to understand how to enumerate the results. So enumeration or enumeration of results can be considered one of the most important parts of probability theory, and this is a related subject in math which is called combinatorics. I guess you have studied like the beginnings of the basics of combinatorics at school. Please answer me. Have you studied them or not? No, you haven't. So before I start dealing with probabilities, I'll give some brief introduction into combinatorics. So combinatorics answers the question how many results or how many systems satisfy some kind of criteria. For example, let's say that we have a set of 3 letters, A, B, and C. And we want to answer the question, how many words can be composed out of these 3 letters? And of course, we need to specify some more conditions. So we need to understand how we are allowed to compose the words with these letters. Well, first of all, let's consider n-letter words in which we allow repetitions. So that means that the same letter can occur in the same word twice or 3 times or even more.
3 power n.
3 power n, so you know. Why?
So on each position we can choose 3 different things.
Yeah. So if you want to explain this in a rigorous way, in mathematics you use a stuff which is called mathematic induction. And you say that if you have previously counted a number of words which are composed of n-1 letters, so we'll call them A of n-1, then how many words will be composed of n letters? Of course, you can take each of these words and add one of 3 letters, A, B, C, and each of these letters will give you a completely new word. So that means that the number of words composed of n letters can be expressed in terms of number of words composed of n-1 letters as follows. A n-1. And then we can continue expanding this equation. So we can say that this is 3 multiplied by 3 multiplied by a n-2, which is equals, and so on and so forth. So we can have here n-1 threes multiplied by a1, which is the number of words which can be composed of 1 letter. And altogether we will have 3 multiplied by 3n times, which is exactly 3 to the power of n. Actually, you can say that this approach, which is called recursive approach, so why it is recursive? Because we express the number which you want to find in terms of number for more simple system, for simpler system. So we reduce, with each step, we reduce the number of letters in the word by 1, and thus we are able to calculate everything. Okay, let's go another way. So let's say we want to find the number of permutations of these 3 letters without repetitions. Permutations without repetitions. So let's say we want to choose 3 letters and make a word out of them, and the word is made in such a way that any letter occurs in such a word only once.
And so the length of the word is exactly 3?
Let's say, yeah, exactly 3. So the length of the word K is exactly 3. Of course, you understand that the length of the word cannot be exceeding 3. So you cannot make a word out of 4 letters if you have only 3 of them, and you are not allowed to repeat them in the word. So,
and sir, if K is less than 3, then can we call it a permutation also?
Yeah, it can also be called a permutation. So when we have 3 letters, actually the number of words is 6. I can even write all of them. A, B, C, okay, B, A, C, also C, A, B, A, C, B, okay, also B, C, A, C, B, A. So altogether I have 6 words, and as Agafy said previously, this number is actually 3 factorial, and factorial is a notation which is expanded in the following way. It's a product of all integers from the number 3 up to 1. So if you have 5 factorial, then 5 factorial is calculated as product of 5 by 4 by 3 by 2 by 1. Now we need to find out how this number can be calculated. So let's say we want to make a word. So for the first letter, we can have one of 3 letters. So we can have A, B, and C. That gives you 3 possibilities. And we have 2 letters left. And for the second letter, we are allowed to choose one of 2 letters. Because we have 1 letter on the first place, that means that this letter cannot be on the second position. So that leaves us with 2 letters. And on the third position, we can only have 1 letter possible. So 3 by 2 by 1. Of course, if you want to calculate the number of permutations of n letters or n objects, then P of n is n factorial. Okay, next step is to calculate number of permutations if we have only m elements which is less than n. Then using the same kind of approach as I have shown previously, we can immediately write that this number of permutations, P of m and n, is calculated as n times n minus 1 times n minus 2 until the last factor in this product will be n minus m plus 1. Or in other words, it can be written as, in a more simple way, as n factorial divided by m factorial. this formula actually has some meaning. And the meaning is as follows. You can consider all permutations of all n objects and then look onto first m of them. Okay, not by m factorial, but n minus m factorial. Excuse me. N minus m factorial. So you write a permutation of n objects, and then you consider first m of objects of them. So that means that the sequence which is in the next n minus m positions doesn't influence your permutation here. So you can say that one permutation of m objects corresponds to n minus m factorial permutations of n objects. So the number you want to find is actually equal to Pm of n, and it corresponds to total number of permutations of n objects divided by the number of permutations per one permutation of first m positions. So this is the answer for the number of permutations. And another important thing about combinatorics is also calculation or enumeration of combinations. Combination is slightly different object from permutation. And the main difference between them is that permutations are ordered sets. So that means that each permutation, the order of elements in each permutation is very important. So when you change the order of elements, then your permutation becomes different. While for combinations are, you can say, disordered, or actually the sets without order. Without order. So that means that you're actually interested in which kind of elements are in your combination, but it doesn't matter for you the order of these elements. So when you change order, it doesn't make a different combination. So you can say of combinations of something like a lottery. So in lottery, you choose few numbers, like let's say 7 numbers, and you want to, for as many of your chosen numbers to coincide with so-called correct numbers. So, and it doesn't matter the order of your numbers. So if you choose them in a different way, then your combination is exactly the same. And in order to calculate combinations, so when you have combinations without repetitions, so the easiest way to calculate combinations is to take a number of permutations and divide them, well, by the number of permutations inside it. So you can say that, okay, so P of Mn is number of permutations of M elements, but inside, in between these M elements, I can arrange them in M factorial ways. And each of these M factorial possibilities represent only one combination. So that means that if I divide the number of combinations by the number of permutations inside, okay, one of the chosen permutation, M factorial, then I will obtain the number of combinations without repetitions. Okay, these are the most basic concepts of combinatorics which will be used for calculations in probability theory. Okay, let's now consider the following subjects. Let's say that I toss a coin 5 times, and I want to calculate a probability that out of these 5 times I have 4 times I have 0 result. So in order to calculate this, we need to calculate the number of sequences of 5 zeros and 1s which contain exactly 4 zeros. Okay, each of these sequences can be described by positions which are occupied by each of these zeros. So for this sequence, zeros occupy position 1, 2, 3, and 4. So you can say that to each of these combinations, I can put into a correspondence a combination of 4 numbers, 1, 2, 3, 4. And this is a combination because order here doesn't matter, because if I choose positions of zeros as 4, 2, 3, 1, it will describe me exactly the same combinations of zeros and ones. So that means that we indeed are dealing with combinations. And here I have a combination of 4 elements out of 5. And I don't allow any repetitions. So that means that I cannot place 2 zeros at the same position. So this is combinations of 4 elements out of 5. So I can calculate them using this formula, which I can further transform as follows, like n factorial over m factorial over n minus m factorial. Or here you can write 5 factorial over 4 factorial over 1 factorial. So what is 5 factorial? 5 factorial can be written as product of 4 factorial by 5. And then I divide over 4 factorial and over 1 factorial. 4 factorial is cancelled out, so that I have only 5 over 1, which is 5. So I only have 5 combinations which satisfy this condition that I have only 4 zeros. I can even write that down all of them. Well, of course, these problems are quite simple when you look at when the numbers are quite small, but when numbers keep increasing, you would not be able to write all of the combinations, and you need to apply these formulas for calculations. Okay, so now we go on to calculation of probability. So the total number of sequences of zeros and ones composed out of 5 symbols are equal to 2 to the power of 5. So because we can have 0, 1 at each of 5 positions, and remember in the previously calculated 3 to the power of n as a number of words which can be composed out of 3 letters, we now have 2 letters and 5 symbols. So I have 2 to the power of 5 of possible combinations, and now I need to, in order to calculate the probability, I divide 5 desired events by 2 to the power of 5 total number of possible events. So this gives me 5 over 32. Now let's consider a slightly different task. So this is, let's say we have a dice. A dice has numbers 1, 2, 3, 4, 5, 6 on its faces. And you can roll a dice and have one of these numbers as a result. And let's say I consider a following random variable, the following random number. I toss a dice for 12 times, and I calculate number of ones which appear during these 12 dice rolls. So let's say n1. This is number of times I have 1 as a result of a dice roll. So I can calculate the probability of each of these n1s. So let's say that if n1 equals to 1, then the probability p1 would be equal to 12 factorial over 1 factorial over 11 factorial.
P1 denotes a probability. By P1 you are denoting a probability.
By P1, yes. By P1 I denote a probability. Yes.
But probability is more than 1.
Yeah, but that is it, because this is not the end. So let's say first I calculate n1. So let's say the number of combinations, the number of combinations in which we have 1 as a result. So we have combinations of 1, 2, 3, 4, 5, 6. So we do this experiment 12 times, and we calculate number of combinations in which I have exactly 1, 1, and all of the other results are different from 1. So I can say that for each of these results, so let's say for the first digit, if it is equal to 1, then probability for it to be equal to 1 should be 1 over 6. And if it's different from 1, so let's denote this number as p. And if it's different from 1, then it's 5 over 6, which is 1 minus p. So this is the probability of this digit to be not exactly 1. So if I want to calculate the probability of the event in which I have 1 on the first position and all other 11 positions are different from 1, then total probability of such event will be 1 over 6, so this is p, okay, p11. This is p multiplied by 1 minus p to the power 11. Or this is actually n minus 1. But this is only one of the possibilities, because if I consider only the results in which I have only single one result, then I need also to consider other possibilities, that I have one result on the second position, during the third row, the fourth row, and so on and so forth. So in order to calculate this P1, for this probability P1, I multiply a number of combinations, C1 of n, multiplied by the probability of each of them, p multiplied by 1 minus p to the power of n minus 1. In general, I can write that if I have a so-called generalized dice, in which I have each of these dices, if I have a desired event with the probability p and undesired 1 minus p, then the probability that my desired event occurs k times during n rows will be equal to c of k of n multiplied by p to the power of k multiplied by 1 minus p to the power of n minus k. By writing this formula, I define a probability distribution. So for each number k, I have a number which is called the probability of this number. So probability of k events happening. And this is called probability distribution. So when I have such a function that I have some random variable, in my case, this random variable is k, that the probability of this event is given by this formula. So this is called probability distribution. And this particular type of probability distribution is called binomial distribution. Okay. So far, we have only considered the case when the random variable can attain only discrete values. So this number k, the number of ones in my dice rolls, can be an integer number ranging from 0 to 6. Okay, from 0 to 12 in this case. And of course, if you deal with real-world situations, you will also be able to have some random variables which don't have discrete set of values. So I can say about this as continuous variables. So let's say we measure a pressure of ideal gas. And we measure this pressure to a very great precision. And we see that this pressure is actually a fluctuation value. And at any given point of time, pressure of gas, P, pressure, is a real value. Well, it's actually a positive real value for the most number of cases, but this is a real value. So you can say that this number can have one of the continuous values. So you can find this value in some range of values. Then how do we describe a probability distribution for a continuous variable? Well, of course, it's impossible to design this type of a function which gives you a probability to have some kind of value. So let's say the probability of the pressure of gas to be equal to the atmospheric pressure. It's 0. Because always, at any given point of time, the atmospheric pressure is a real value which has infinite number of digits. And if the pressure of gas has only one different digit from P0, then we don't have equality. So it's very easy to achieve inequality between the pressure of gas and atmospheric pressure. So it's impossible to have such a function. Instead of this function, we have a probability density function. Probability density function. How this probability density is defined? Let's find the probability that pressure of gas is in between P0 and P0 plus small dp. Of course, if we have larger interval, then the probability that pressure falls in this interval will be greater. So let's say that if I have probability that pressure is in the interval from P0 to P0 plus 2 dp, so let's say this is probability. This probability should be equal to the sum of probabilities. So I can divide this interval by 2, and the total probability will be sum of probabilities that this number falls into one of these two intervals. So you can say that the probability is actually, if the length or the size of the interval is very small, then we can say that probability is directly proportional to the size of interval, dp. And this is actually a probability, the coefficient of proportionality is called probability density. So I can write that this is rho of P0 multiplied by dp. And this is the probability of pressure being in this small interval from P0 to P0 plus dp. It's often called dp in order to underline that this probability is quite small when the interval which we consider is very small. Then I write for this probability dp. So that is how we deal with continuous variables. Instead of probability distribution function, we have a probability density function. Now we are going to study a few important quantities which are associated with probability distributions. So if you know a probability distribution, you can say that you know almost everything about your chaotic system or about your random variable. But some particular quantities are of great interest. Sometimes we are interested in them even more than in probability density functions. One of these quantities is mean value. So let's say we have random quantity x, and mean value is by definition a following. If x is discrete variable, then this is sum of pi over multiplied by xi. So pi is probability of x being equal to xi. So for your coin, if we have numbers 1 and 0 with probabilities of 1 over 2, then average or mean value is calculated as follows. I multiply probability of 0, which is 1 over 2, by 0, plus probability of 1 by 1, and get 1 over 2. This is average or mean value. Another important quantity is variance. Variance describes how your random values are deviating from mean value. So of course, you can calculate for each, so you produce some random events, and in each of these events you have the result of xi. Then you calculate difference of xi and x, and if you take mean value of this quantity, you will get 0. So mean value of this quantity will be 0. Because your quantity can be either greater than average value or lower than average value. So this difference can be positive and negative. And altogether, positive values are compensated by negative values, and on average, this is 0. So this quantity, this deviation, average deviation, cannot describe you the dispersion of xi value. But in order to calculate variance, you do the following trick. You abandon a sign of this difference by squaring this value. So you calculate a square difference between your random variable and mean value of this random variable. So that So average square of deviation of your random variable from mean value gives you variance. And if you take a square root of variance, you will get a standard deviation. So let's calculate the standard deviation for a coin. Okay. So standard deviation for coin is equal to the average of x minus x mean squared, and as any average, it can be calculated in the following manner. So this is sum, or instead of sum, I can write with probability 1 over 2, this x value will be equal to 0, minus 1 over 2 of mean value squared plus 1 over 2, with probability 1 over 2, you have 1 as a result of coin toss. So at the end you have 1 over 2 multiplied by 1 over 4 plus 1 over 2 multiplied by 1 over 4. Altogether it gives you 1 over 8 twice. So this is 1 over 4. And standard deviation is given by as 1 over 2, a square root of 1 over 4. So you can say, yes, of course, so if you have 0 and 1, each of this value is separated from mean value by 1 over 2. So this value of standard deviation indeed describes you how well your random values are located near the mean value. In case of continuous variables and probability distributions, probability densities, you need to modify formulas for calculation of average value and variance. So for continuous variables, the average value x average is given as follows. This is integral of probability density of x multiplied by x multiplied by dx. And this is, let's say, from minus infinity to plus infinity. In general, of course, the limits of integration are from minimal possible value of x to the maximum possible value of x. And similarly for the standard deviation and variance. So the variance of the number x is given as, again, integral from minus to plus infinity, rho of x multiplied by x minus x average squared and integrated over the x. And there is one important theorem about variance. This theorem can be written as follows. So if you want to calculate variance of some random variable, you can calculate average square of this variable and then subtract squared average of this variable. Let's check this theorem in this case of coins. So squared average of coins, so that is 1/2 multiplied by 0 squared plus 1/2 multiplied by 1 squared. Altogether this gives you 1/2. Then average value squared gives you 1/2 squared. This is 1/4. And then for the variance of the value x, we have 1/2 minus 1/4, which is 1/4. Indeed, this formula is okay here. Okay, how much time do I have left? 16 minutes. Okay. So now I give you a derivation of this formula. If you have missed this previously, these horizontal lines denote average. So this is the operation of averaging. So under the horizontal line, I have random variable. Here, x is random value. Then I do averaging. So here, x is random value. I do averaging and obtain x average. Then I take x minus x average, bring it to the second power, and then again take average over multiple different values of x. And this gives you again the average of squared deviation from mean value. Okay, let's calculate x squared average. Well, first of all, let's calculate x squared. So let's say that x is actually equal to the mean value of x plus the deviation from this mean value. Then let's take this to the second power, and we get x average squared plus x minus x average squared plus 2x average multiplied by x minus x average. Yeah, this is. And then we take average of both sides of this equation. Okay, this one is the mean value squared. The next value is by definition a variance of x. And the next value contains product of some constant by random variable. So we can take this constant out of this average. And then we continue. So now we have something interesting. We have x average average. Okay, x average is constant value, but when we take average of constant value, it remains the same constant value. So we can take out the second averaging sign from here, and then we have difference x average minus x average, which is exactly 0. So this ends the proof of the theorem. So indeed, the average of squared value is equal to the squared average plus variance. Now we are going to the essence of thermodynamics. So previously I have introduced you some concepts of probability theory, and this part of this lecture might be quite boring because we have lots of technical stuff and we have some computations, and how is this related to thermodynamics? In thermodynamics, we study the behavior of many molecules. So let's say we have a huge number of molecules n, and if you remember, the order of number of molecules can be given by Avogadro number. Of course, we are not restricted to this value, but this number gives you some kind of a meaning of the huge number of molecules. And let's say each of these molecules, we calculate the velocity of these molecules. Or let's say not we calculate velocity, we calculate something meaningful. Let's say we calculate a kinetic energy of the molecule. So we can calculate kinetic energy of first molecule, of second molecule, third molecule, and so on and so forth, up until the kinetic energy of nth molecule at some given point of time. Each of these kinetic energies is, of course, a random variable. And these random variables are distributed over a broad range. So the kinetic energy of the molecule can be quite small and it can be quite large. But let's say we want to calculate how total kinetic energy of this gas behaves as a random variable. So we calculate total kinetic energy as K1 plus K2 plus so on and so forth plus Kn. And we want to know properties of the total kinetic energy of molecules K. Okay. We can first take average. So the average kinetic energy of gas is given by sum of kinetic energies of each molecules. And we can say that all of these kinetic energies of each molecule are characterized by some probability density function rho k. And of course, from this probability density function, we can determine mean value of k and also variance of k, or standard deviation of k for each of molecules of gas. And since this probability distribution is wide, that means that we can say that the dispersion, or this variance d of k, is on the same order as k average squared. So to give you a concept of wide distribution, the distribution between 0 and 1 is called wide because the average value is 1 over 2 and standard deviation is also 1 over 2. So we have a standard deviation on the same order as average value. So that means that these values are distributed widely around the average. Okay, total kinetic energy, average value of total kinetic energy can be given as multiplication of n, kT, In by kinetic energy of one molecule, average kinetic energy of one molecule. But what about the variance of total kinetic energy? In order to understand how variance of total kinetic energy behaves, we first consider one explanatory problem, which will help you to understand what happens in this calculation. This is the problem of drunk sailor. So let's assume that we have a sailor which gets out of the bar near the morning and wants to go home. And each 5 seconds, this sailor moves by 1 meter in a random direction. So he can move either to the right, either to the left, with equal probabilities. And we want to find out the distance of sailor from the bar after some amount t has passed. Okay, we can write the following, that at r equal to t, we can actually say that we watch over the sailor at moments of time which are given by the following formula. So we look at where the sailor is at integer multiples of tau. And in each of these moments, we can say that the position of the sailor can be calculated from the position during the previous observation, and then plus some random variable AI. Okay, A maybe n minus 1. This is a random variable, which can be equal either plus A or minus A. So if we take average from this expression, we get the following. Average of n tau is equal to the average r of n minus 1 tau plus average of a n minus 1, and this value is 0. So that means that the average displacement of sailor from the bar is 0. So is equal at each of these moments of time, and we can continue this expression until we reach r average at 0, and at the moment of time t equals to 0, the sailor is at the initial point. So that means that this value is 0. So averaging over this random quantity gives us no information about movements of sailor. We need to do something else in order to find out how sailor moves from one point to another. Let's consider how squared distance from the bar behaves as a function of time. Then let's take average of this number. Okay, since this random quantity can take either values minus a or plus a, then average squared of this quantity will be always equal to a squared. And this one we have calculated previously. Both the first term, both the first factor and the second factor of this expression are equal to 0. So that means that with each next step, the average square of distance from the initial point increments by constant value. So after continuing this expression further, we get the following formula for the average distance from the initial point. We can say that squared distance from the initial point behaves linearly with the number of steps. It's quite an unusual behavior, I would say, because if the sailor moved in one direction, let's say that the sailor always moves to the right, then if sailor moves to the right, if sailor moves in one direction, then this distance r of n tau will be equal to NA, and squared average of this distance, of course this is not completely random variable, it's determined variable, but we can look at this determined variable as a random variable and calculate squared average of this one, and squared average of this variable will be equal to actually squared variable, and it will give us n squared a squared. So the difference between chaotic behavior and determined behavior is in the power law. So when we have a chaotic behavior of sailor, this distance increases linearly, so proportionally to the first power of n. But when we have a determined motion of sailor, then this distance increases as squared n. So by looking at this quantity, we are able to get something about the characteristic of motion of sailor. So if we observe some kind of motion and we don't know whether this motion is directed or this motion is chaotic, we can make an observation and look at this squared average of distance. And if this distance increases with time linearly, then we have chaotic motion. But if it increases using a second power law dependence, then it's a determined motion, so motion in one direction. Now with this explanation given, I return to the subject of standard deviation of kinetic energy, of total kinetic energy. Okay, so here we can actually look at these differences between K1 and K1 average as motions of, as movements of drunk sailors. So K1 can be either greater or less than K1 average. So that means that we indeed have some kind of chaotic motion in terms of K1 minus K1 average. So the difference between total kinetic energy and average kinetic energy. Okay, this stroke is bad. This one is too. Okay, this one is good. Is given by the following sum: K1 minus K1 average plus K2 plus K2 average plus so on and so forth plus Kn minus Kn average. And each of these quantities can be considered as steps of drunk sailor. Well, of course, if we take average of this equation, we will get 0 in both left and right sides. So what we need to consider is squared average. So is average of squared value. Then, using mathematical induction, I can show that this value is actually equal to K1 minus K1 average squared plus so on and so forth, plus Kn minus Kn average squared. Or I can actually do this in this manner. So total kinetic energy minus average kinetic energy squared, average, is given as total kinetic energy without nth particle number n, plus and plus this unusual subscript T reverse slash and then n in figured brackets means total minus nth particle. Okay, again, as previously we have seen this product on average gives 0. And then we can exclude n minus first particle, n minus third particle, and so on and so forth. And we arrive altogether to the expression that the total average is given as n multiplied by K1 minus, so I can say K minus K average squared, and again averaged. So this is n times the variance of kinetic energy of one particle. If we look at the standard deviation of kinetic energy, standard deviation of total kinetic energy then we can write that this is square root of n multiplied by standard deviation of kinetic energy on one particle. And then if we look at a relative deviation, so relative deviation of total kinetic energy from its average value, which is equal as defined as ratio of standard deviation to the average kinetic energy, total kinetic energy, then we get this expression, 1 over square root of n multiplied by standard deviation of kinetic energy of one particle divided by the average kinetic energy of one particle. So you can see that if the number of particles is very large, then even if initial probability distribution can be called wide, so when in the initial, so the kinetic energy of each particle is a chaotic value which can have a broad range of values, but when we look at total kinetic energy, then relative deviation from its average value becomes very small. So you can say that if the initial probability density of kinetic energy of each of the particle, let's assume it looks like this. Okay, this is K, and this is probability density, rho of K. So if the initial distribution of kinetic energy of particles is wide function like this, then the probability density of total kinetic energy is a very sharp peak with very low widths here. And this is what enables thermodynamics. Despite quite chaotic behavior of each molecule, when we look at average numbers over a large ensemble of molecules, then these quantities taken as random numbers have very sharp probability distribution. So you can say that the deviation from average is very small. And that's why even if the momentum transferred by each molecule of the gas to the side wall of the vessel inside which this gas is located can be, okay, average, so it can be some random number. But when you calculate total pressure exerted by gas on the vessel side walls, then this number becomes a well-defined number. So this number deviates from its average value only very slightly. Okay, this is a very important law of probability theory which concerns thermodynamics. More importantly, we can even calculate the probability density function. There is a theorem which is derived in the probability theory, and it says that if we have a sum of large number, x is a sum of large number of random variables, each of them being independent from other values, so sum of large number of independent variables, then the probability density function of the sum of these numbers is given by so-called normal or Gaussian distribution. The best property about this is that it doesn't matter how probability density of each of this term looks like. So the probability density of each of these terms can be any arbitrary function, but the probability density of some of these variables is normal distribution. Okay, with this I think I would like to finish.